Assalamualaikum and a very good evening everyone. So today we're going to continue what we have left from last week, and today basically we're going to cover two parts. The first part will be on interfacing your 68K with your parallel interface and timer, and the second part of this lesson we're going to look at on the microprocessor execution time, in which you're going to see how to calculate the execution times of a certain command or certain codes that is in your program. So without overdue, let's go into the first part of this lesson. So before I start with this your last lecture for today, I just want to highlight that for this chapter, basically it's a long chapter, but I'm going to cut it short, in which some of the part in this chapter I will not cover it. Okay, will not be covered today. Why? Because I guess some of the parts written in this chapter, some of the content in this chapter is quite overwhelming, and you will not be using it in your PBL, and it will not be coming up in your final exam. So I'll be covering only of the necessary part of parallel interface and timer. If you want to study by yourself, you can always look at these slides, the chapter 11 slides, and go through by yourself. Okay, so let's start on what is this serial and parallel mode of transferring data. So as you aware or you are not aware, there's two modes in transferring data if you are using a computer. The first is through serial communication, and the second is through parallel communication. Nowadays, in this modern type of computer architecture, most of the communication is being done serially, because we have the technology to create faster serial communication, like your USB, for example, and your serial port. Most of them is using the serial communication. Okay, but last time, before modern computer exists, okay, before your current computer exists, the means of faster transferring data is using parallel communication instead of serial communication. So what is serial communication? So serial communication, as the name implies, you have like a line, like in this diagram. The data is being transmitted one by one on the serial line, on the serial interface. Okay, so you can imagine the serial line I mentioned just now. It's just one wire to transmit all of the data from one computer to another computer. Okay, whereas in your parallel communication, you have multiple parallel communication interface, so you can send more data at once. Okay, you can send a lot of data at once using this parallel communication. So example of parallel communication last time is you have this parallel port at your PC, in which it is used to connect printers to the port, okay, to your PC. So that is the difference between serial and parallel communication. But nowadays is very hard for you to see this parallel port and everything, because nowadays everything is switched to serial communication. Your USB, your Thunderbolt, everything now is serial because it's much more easier and it is much more compact, doesn't require large cable. So things are switching to serial communication. But I guess inside your computer, the communication using from one component to another component, for example from your RAM to your GPU to your CPU, is still using parallel mode of transferring data, parallel communication. So parallel input and output allows all bits of data to be transferred simultaneously. So it is faster than serial data transfer. To ensure data that transfer is correct, hands-shaking signal is usually represented by strobes or by clock pulses. One device capable of performing parallel input-output is the 68230 parallel interface timer, PIT. So here it say that the mode of the mode of transferring data using parallel communication is faster, but this is, I mean, we are talking about 68K. This is like the 40 years ago, the technology that exists 40 years ago. During that time, yes, the parallel modes of transferring data is faster, but currently serial mode of transferring data is also fast. Okay, but just bear in mind that we are talking about 68K. In 68K, the mode of transferring data using parallel communication is still faster. So one device that we use to interface with the 68K in order for us to perform this parallel communication is called 68230 PIT or 68230 parallel interface and timer. So this is the picture of the parallel interface and timer. Okay, so what is this 68230 PIT? So it's a general purpose peripheral, meaning that it is for general purpose. It's not for a fixed purpose. You can use it for many things. Its primary function is an 8-bit or 16-bit parallel interface. So if you want to connect to some device parallelly, okay, using a parallel interface, you use this chip. And it has another function, which is you can program it as a programmable timer. Contains 3 8-bit parallel port. Okay, we have 3 parallel port A, port B, and port C. The parallel interface is divided into 4 modes with various handshaking and buffering capabilities. Okay, the interface is divided into 4 modes. It can be unidirectional 8-bit or 16-bit, bidirectional 8-bit or 16-bit, and the programmable timer can be used to provide many services like periodic interrupt generation, square wave generation, and time measurement. So this is the pin assignment of 68230 PIT, and this is the internal arrangement of a PIT, as you can see. So similarly, if you want to interface this PIT with your 68K, we are using what we call as a memory map. Okay, memory map interfacing, like how you interface your input output and your memory to your 68K. It's the same thing. So when I say memory map address space, so you got to remember that you are allocating some memory space inside some region inside your address space for this particular peripheral, for this PIT. Okay, so it's like this. So remember back, you need to have your base address and the size that you're going to allocate for your PIT, and then from that we are going to design the decoder. We're going to see which pin in address bus that you're going to use to connect to the decoder, and so on and so on. So that's all for your PIT. Okay, so I'm going to, for this particular slides, I'm going to stop here. So if you want to go into detail on like how to program your 68230 PIT, you can fairly check by yourself. Okay, so how it's connected to the data bus and everything, how the handshaking is accomplished. I think if you want to go into detail, you can see it by yourself, this slide. But now what I'm going to do is I'm going to go back to the previous slide, chapter 10, and we're going to look at how we're going to interface your 68230 with your 68K. So basically the way we are doing this step is fairly simple, is similar on how you're going to interface your 68K with your memory. Okay, so there's nothing complicated about it. So here currently this is a simplified pin assignment diagram for your 68230. Okay, so again you have your register select pin. So not again, this is fairly new, this only appears today. So in your 68230 parallel interface timer, you have what we call as a register select. So if you remember back, just now, the 68230 have few registers that you can select. Okay, few registers that you can select. Where is it? It's not. Okay, this part here, register select logic. So the register select part is the pin that you're going to interface with your address bus. Okay, your address bus. Address bus. And then similarly, you have your data pins connected to a data bus for unidirectional data transfer between the 68230, your 68K. And then we have chip select over here, read and write, to specify whether you are writing to this PIT or you are reading from this PIT. And that's all, I guess. Okay, so the way we connect your 68K to your 68230 is very simple. It is similar to how we connect this to your memory. Okay, again, if you are using partial addressing mode, you're going to have your address decoder over here. Okay, you have your address decoder over here, and then the address bus is connected to the address decoder, and then this is going to be connected to the chip select. And then you have your UDS LDS. If you remember back, UDS LDS is the first bit on the address pin. Okay, and then data pin is connected to the data bus, and detect is connected to detect, and read and write and such, and etc. Okay, so let's look at an example. Okay, question: a system containing total of 32 kilobyte of ROM with base address 000000, a total of 128 kilobyte of RAM with base address 400000, and a PIT with its base address 800001. Design a partial address decoder using 74LS138 for this system. Note, this PIT will occupy the memory map from address 800000 to 80003F. The register select pin RS1 to RS5 of the PIT is connected to A1 to A5 of the microprocessor's address bus respectively. So what are the steps? What are the steps in designing a system which consists of this device listed here and your 68K? Okay, so the first step, as I've showed you last time, and if you can remember clearly, for each of the device, your ROM, okay, your ROM, this is number one, your RAM, your PIT, you need to determine its base address. This is given by the question, or this is being set by you. Okay, and then you're going to determine the size for it. Okay, but for the PIT is already given the start address and your end address. Okay, and then lastly you got to find the end address. Okay, how are you going to find the end address? Simple, your base address plus the size in hex minus 1. So you'll get the end address for each of the component. But for the PIT is already given. It's already given at 80003F. So then what do you do? Once you have figured out this part, you're going to create a table. Okay, you're going to create a table. Okay, this is also covered last time in memory interfacing. Okay, look back at the video if you don't understand, and study again the slide if you don't understand. I'm going to go this very quickly, because this already been covered. So what do? You have your start address in your end address here. Okay, start address and end address here. Create this table, and then you're going to see, translate the address range over here into binary numbers. Example 000000 corresponds to 00. Sorry, I'm afraid that you might lose it over here. Okay, this part here, this part 000000 corresponds to this part here, 0 0 0 0 0 0. Okay, and then whereas the 007FFF is here, 0 0 7, and subsequently FFFF. Yeah, so 007FFF. So that's how you figure out the binary number for your base address and your end address. So maybe I can write this down again. This part is 007FFF, whereas the top part is 000000. So take 4-bit and turn it into your hexadecimal. So from there you're going to identify, okay, the third row over here, you're going to identify which address pin that changes. Okay, that changes from 0 to 1, and all of the address pin that changes from 0 to 1, you're going to denote it by X. So again, like last time, except for this A0, yeah. Why? Except for this A0, this is connected to your upper data stroke, and your lower data stroke. So we are denoted by hash here, hash symbol. So everything else that changes 0 1 denoted by X. This also changes 0 to 1 denoted by X, changes 0 denoted by X, and so on and so on. So you have all of this part that changes. We're going to specify this as the pins that is going to the address bus directly to the peripheral. Okay, so this goes to the directly to the address bus connected to the peripheral. So you do that again for the next two devices, your RAM and your PIT, and then you're going to find out that the pins that doesn't change, okay, the pins that doesn't change is this part, yeah, this part, all of this part here. So the pins that doesn't change the address, the value. So because the question here specify that you need to use 74LS138. So if you remember back, your 74LS138 consists of three inputs. And it will decode from the 3 input into 8 output. So you need to specify from here. You need to be clever about this. You need to be like a bit smart in figuring this out. From all of the unused address pin, which 3 pins, because the input to 74LS138 consists of 3 inputs, which 3 pins can be used to select peripheral that is talking to the 68K. So I hope you understand what I mean by that, because you have your address decoder now. The address decoder will select which device is connecting to the 68K. So you need 3 pins that changes its value, that can be used to connect to the address decoder. So if you look at the last 3 pin over here, if you use these 3 pins, we can actually select which device, we can specify which device I'm going to use to talk to your 68K, okay, by using the last 3 pin over here. So that is what we're going to do. So taking the A21 up to A23, we're going to connect this to your 74LS138, okay, and then based on the value, we can specify the output to be connected to ROM or RAM or PIT. So some of you might be wondering why there's 274 LS138 that we are using. So remember back, everything that is a memory device consists of even and odd address. Okay, so we are using this to select the ROM for even. This is the ROM for odd. If you see here, even, odd. Okay, RAM, even, odd. Okay, but the second 74LS138, we have the connection number 4 here connected to your PIT. So that's the reason why there is a 274LS138 over here. So if you look back, if the value of A21, A22 and A23 is 000, meaning that the 74LS will be selecting Y0 here as an output, because 000 is 0, so only Y0 is while 0 is selected. If it's 010, 010 in decimal is 2. Okay, so 2 is selected. Okay, previously is 0 and now 2 is selected. If the input of A to 1 to A to 2 and A to 3 is similar to the states of this binary over here. Okay, so if it's 001, so if it's 001, so 001 in decimal term is 8. So therefore, my mistake, 001 is 4, means that pin number 4 here is selected to be interfaced to your 68K. Okay, so depending on the states of the pins to the address decoder, we will select which peripheral that we are going to connect to your 68K. So I guess that's all for the first part of this lesson. Okay, so that is on interfacing your parallel interface timer with the 68K. Next, what we're going to look at is the microprocessor execution time. So we're going to continue with the second part of this lecture on 68K instruction execution time. So the objective is for you to be able to understand the timing instruction and the syntax execution time. Let me just check whether I'm recording or not. Okay. So the 68K instruction execution time, you can get the execution time for a particular command or particular code in 68K in your assembly programming. Is written in the datasheet. So normally it is shown as this notation, and with bracket R /W. So n here is the total number of clock period, R is the total number of read cycle, and W is the total number of write cycle. So let's say that from your datasheet you want to look at a particular command. So in your datasheet you will list all of the instruction execution time, and then you check like a particular command like this, for example, it move from the data register to an address register, this one. So if you see, like, it's written 18 3/1. 3/1 means that the total number of clock period to execute that particular instruction is 18 period. So for this particular command, move from the data register to the address register, 1831. So a total number of 18 clock period is required for it to execute the command. So from the 18 clock period, you have, because inside here is written the number of the read cycle and the number of write cycle is needed to read and write from the data bus. So we have a total of 4. 3 plus 1 is 4. 3 plus 1 is 4. Okay, total of 4. So 3 out of 4 from this 18 clock period is used to read from your data bus for the read cycle. Okay, So 3 out of 4 from 18 you have 12. Correct. Okay, and then the remaining 4 period are used for your right cycle. Okay, so and the bus idling is for 2 period. So I made a mistake just now. It's actually not 18, it's 16. Why? Because of this, out of this 18 clock cycle, 2 are used. Let me write this correctly. From the 18 clock period that you are using, okay, so you have 18 total number of 18 clock period. So here 2 are used for the idling, bus idling. 3 out of 4, which equate to 12, are used for the read cycle, to read from the bus, and the remaining 1 over 4, okay, 1 over 4 times 18, the remaining 1 over 4 times 18, the remaining 4 period, the remaining 1 over 4 times 16. Sorry, this is not times 18, this is times 16, so I make a mistake again. The remaining 1 over 4 times 16, you get 4. The remaining 4 is used for your right cycle. Okay, 4 period used for your right cycle, and 2 is for the idling of the bus. Okay. So you can imagine like 18 clock cycles, okay, 18 of this clock cycle is used for the instruction just now. Okay, and depending on your oscillator, it will give a different length of time. So meaning that if you are using 10 megahertz clock oscillator, okay, which is the maximum for 68K, the time period is 0.1 second. This is for 1 clock cycle. So meaning that if you want to calculate the total duration for the execution of the instruction, over here it is 0.1 microsecond times by 18, so you have 0.18 microseconds just to execute the instruction just now. So that's how you calculate the execution time of your command. Okay, so again, just now, sorry, I make a mistake. You need to include the bus idling period if you want to calculate. Bus idling period is 2 periods out of this total number of clock period that is listed in your data sheet. So if you see the data sheet, okay, the number of clock period required is differ from instruction to instruction, and the type of data being executed. Okay, for example, if you are moving from a data register to a data register, then you will need a total of 4 clock cycle, with 1 clock cycle is used to read from the data bus, okay, and 0 clock cycle is used to write, because there's no this is only reading from the data register, right? So there's no writing to your buses, so that's why it's 0. And the remaining 2 is for your idling, bus idling. So you can see from this table, the data from the data sheet, okay, what is the total number of clock period required to execute a particular instruction. So table 83 shows the execution time for you to move along data from particular source to a particular destination. So depending on the instruction and depending on the types of data being transferred or being executed, you have different clock cycles, that is different clock period that is being executed. So this is on the immediate instruction execution time, like add. Okay, if add byte word size, what is the execution time required? Okay, if long, what is the execution time required, and so on and so on. Okay, you can see over here. And then branch conditional instruction execution time, like your branching, branch to subroutine and branch always, your BCC is all listed over here. Okay. How many clock cycle is required for it to execute this particular instruction if it is in a byte size. And it's pretty much straightforward. I guess you can understand this by yourself. Okay, let's look at an example. Okay, let's say you have this particular subroutine over here, you want to calculate the execution times of this particular subroutine. So we're going to do that. So the way we do that is, first you need to see from the data sheet just now, from the table just now. For example, moving along instruction, from this number, load D6 is this number, how many clock period does this require? So we check back on the chart over here, moving a number from what size is that, long size, to a data register, how many clock cycle required? Okay, long size, if I'm not mistaken, right? Yeah, to D6. So this required 12 clock cycle. Okay, this required 12 clock cycle. Okay, from a number to a data register, long, sorry, so I'm saying this one. Okay, this one over here. So 12 clock cycle is required to execute this particular instruction. Then we move on to the next instruction. What is the next command or code? Sub I long word 1 from a data register. So sub I, sub immediate. What is the clock cycle? How many clock cycle is required for that purpose? Okay, 16. So how do you get 16? So you see, you are executing long word, so you need 16 clock cycle to execute this particular instruction. Okay, so this 16 clock period is required to execute this particular instruction. Then the subsequent command is pretty much straightforward. Branch on equal, you look back, branch on equal over here. So see, this is branch taken, branch taken, if because this is a branch command. Okay, if the branch is taken, then it will execute 10 clock cycle, 10 clock period. Okay, if it is not taken, then it will execute 8 clock period. So if it's taken, 10 clock period, not taken, 8 clock period. And RTS, return to subroutine, required a 16 clock period. So RTS, where is RTS? Is it listed over here? RTS 16, yeah, RTS 16 clock period is required. Okay, so if you want to calculate for one loop, because this is a looping program, because you have branch on equal, if meaning that if it's 0, then it will return to your subroutine. Then if it's not 0, it will jump back to deal 1. So it will keep on minusing 1 to D6 until it is 0. So this is a loop. So one loop, how many clock cycle does it require to execute this one loop is so you're going to look at later on how you're going to calculate that. Okay, so this is as was shown to you just now, how to get one execution time. Given the clock is at 10 megahertz, then one clock period, so this corresponds to one clock period. So you have your clock period, okay, so this corresponds to one clock period. This corresponds to one clock period, means that if we are taking from here, so this to this, okay, so this is what we call falling state, okay? Falling to falling. If you are taking from rising to rising, then the same, okay? So for 1t over here, it will take 0.1 second if you are using 10 megahertz clock, okay? So one period will give you 0.1, sorry, this is 0.1 microsecond, not second, 0.1 microsecond. So how many periods to get 1 second? So because this is already like frequency, frequency, because if we state here 10 megahertz, 10 million hertz, meaning that in 1 second there's 10 million period. So 10 million period. So but then if you know the period, what's the period, that you can always divide this by 1, okay, 0.1 micro, you will get the total number of period on 1 second. So this is the total number of period in 1 second. In 1 second. Okay. So going back to the question just now. Okay, the question just want to show, because it's not listed here, actually the question want to ask you, in 1 second, so in 1 second, how many loop can this subroutine execute? So how many loops does this subroutine execute? So if you, the way you calculate that is, first you need to list down all of the clock period required in the subroutine. So we have 12 here, starting from this smooth L, and then 16 plus 10A. So why do we have 16 plus 10 times A here? So because here, starting from this loop, starting from this command, okay, sub I BNE, if your D6 is not 0, you will keep on looping. So you keep on looping. So 16 is sub I, then you have your BNE as 10, because if you keep on looping, then we multiply it by A, which the A is the time loop. Okay, once the loop has been executed, you will go down, okay, you will go to this part, you will not take the branch not taken part, which requires an 8 cycle, and then it will take the return to subroutine, we will execute the return to subroutine command, which requires a 16 clock cycle. So how many loops in 1 second? The question is, how many loops can this be executed in 1 second. So we already know that if we are using 10 megahertz clock, means that in 1 second there's 10 million period. Okay, so 10 million period of clock cycle is equal to what we have calculated just now, what we have listed just now. Okay, so if we equate this, we get like 10 million is equal to 36 plus 26a, and then 26a is equal to 10 million minus 36, and then you can calculate this by yourself. So this is the time loop, the number of loop that is executed within 1 second, provided that during the 1 second period this has not been has not finished executing. Okay, if this finish executing within 1 second, then there's no point of calculating this, correct? But we want to we assuming that during this 1 second, okay, during this 1 second, this has not been executed. What is the number of loop? What is the number of loop executed during that 1 second? Okay, the number of loop here is denoted by A, time loop. Okay, so that's all, I guess, for calculating microprocessor execution time. With that, I think your syllabus has finished. Starting from next week, we're going to look at on your PBL. So basically PBL, you're going to do your mini project and the instruction will be given to you later. So if you have any question, you can always directly ask me through Microsoft Teams or WhatsApp or whatever means that you can you prefer to communicate with me. If there's no any question, then I will see you next time. Thank you very much.